Hello, Honors Chemistry students. This is Mr. Tro coming to you. I'm here to introduce you to the final lab in Unit 9 on solutions. Unfortunately, due to our e-learning situation, you won't be able to physically do the lab, but I wanted to record this video as an introduction to give you kind of the baseline that you'll need, some background information, so you could complete the lab virtually. Not so much do the lab, but at least look at the procedure and then look at the data that I provided for the lab, which is attached to this PDF you'll get off Schoology on page 3. And hopefully this video will help you understand what you would have seen if you were in lab, so that you can go through and at least get something out of it. So, first of all, this is lab 4. It's freezing point depression. In class we talked about colligative properties. One of them was freezing point depression and one of them was boiling point elevation. So in this lab we're doing a similar thing to what we did earlier in the unit. If you remember, we did a lab earlier where we did the freezing point of water. We did freezing and melting of water. And if you remember in that, if I'm just going to trace it here in a highlighter, if you remember in that one, we started water at about room temperature and then we cooled it down in an ice salt water bath. And it did a little bit of maybe supercooling, and then it kind of stayed level here at 0 degrees, which is the freezing point of water, and then it eventually dropped off. And that's what we saw when we froze the water. And if you remember, we did another, we stored that run and we did another run, and we warmed that water up, and then it melted, and then it went back up again as it was melted and started warming up to room temperature. So if you remember that, you're actually in pretty good shape to understand this freezing point depression lab. So basically, we are not going to be doing water in this lab. We're going to be doing two different solutions. So simultaneously, in the same salt ice bath as before, we would be cooling down two different solutions. Now, if you look here, the solutions are clearly labeled in the lab. Solution 1 and solution 2, and it shows you how they're made. Antifreeze is something called ethylene glycol, and it is actually outlined in the lab for you. It gives you the chemical structure of ethylene glycol down here. It's otherwise known as antifreeze, but it gives you the chemical formula for ethylene glycol, which means you could, with the periodic table, find the molar mass of ethylene glycol. We could certainly do that. And you will be doing that eventually in the lab here in the analysis portion or in the data portion. You will be looking up the theoretical mass of ethylene glycol off the periodic table. But the nice thing, or the cool thing about this lab is that we are going to actually track the freezing points of these two solutions as they freeze. And from that information, coupled with freezing point information, coupled with the concentration information we have here, if you see, it actually gives us the mass of solute in the mass of water. So you have the ability to turn this mass of solute and this mass of water into the two different units you would need. Maybe it's moles of the solute, maybe it's kilograms of the water. You'd be able to figure out different units you might need. I don't want to give you too much information right now because that's something you're going to have to work through in the analysis portion. But you would be taking these two solutions. Obviously, one of them is double the concentration of the other, and you would be putting them. If you read through the procedure, I'm going to generally go over it here, but you would basically be putting about 5 milliliters of each solution into a test tube. So you'd have two test tubes, the same depth of solution, and into each test tube you'd be putting a temperature probe from the actual LabQuest, which you've used before, and then you would be sticking both of those test tubes into an ice water salt bath. Okay, so this whole portion here talks about making your ice water salt bath, which you've done before. You did this with the melting and freezing of water lab. And we would get it down to probably -10 or -8 or -10 degrees, which would provide us with plenty of, for lack of a better term, coldness for the lab to happen. You would change the mode on the LabQuest so that it runs long enough as it collects data. And basically, you would stick those 2 test tubes into the ice salt water bath, and you would gently stir them. You would gently jostle the temperature probes, and you would track their temperatures, the temperatures of solution, while it was freezing. Generally, you would see a curve that looked like this. As time goes on, you would see that the temperature, unlike before, if you remember before when it was pure water, it kind of stayed level, and then it dropped off when it was all frozen. And we talked earlier, we know that this point right here was called, this was a change, this was actually the freezing process, okay? It's a little different now. What you would see in this lab is a little different. You no longer have a slope of 0. You no longer have a flat slope while it's changing, while it's freezing. You are actually going to have a negative slope. All right, and that's actually important to understand. It's important to understand that because think about what's happening as your solution, right? So say you have a test tube and you've got your solution in it. There's your ethylene glycol, right? And as that solution cools down, there's going to be water crystals. There's going to be water that starts to crystallize out. So let these blue dots represent crystallized water, okay? So that is water that was once part of the solution, that was solvent that was once part of the solution, that has now been crystallized out of solution, and it's now a solid. So if you remember back to the definition of a solution is a homogeneous mixture, okay? It's evenly mixed. If we are looking at these crystals of ice, you can ask yourself the question, are they part of the solution anymore? And the answer would be no, they're not. Since that water is crystallized out, they're no longer part of the solution. So think about the equation for molality, right? It's moles of solute over kilograms of solvent, which in this case, let's call it water. Well, as water starts to crystallize out, what does that do to this value right here, the value of water that's still liquid solvent? Think about that for a second. Right? Hopefully the answer you came to is the fact that that value is going to decrease. Okay? So as that value decreases, so as this, right, as this value drops, think about what that does to the overall molality of the solution that's left, the solution that is not yet frozen. The overall molality is going to change. So that's up to you to determine whether that molality is going to go up or down. But hopefully you can understand that the kilograms of water, liquid water in that solution is going to decrease. Okay? Now, because of that, I'm going to be erasing things as I go, but you can certainly rewind this video and watch it again. Because of that, right, there's going to be an impact on that slope. It's not going to be flat anymore, right? That slope is going to start to change, right? So instead of being flat and then dropping down, you're going to have this area here. You're going to have this area here, right, where it's not staying flat, but it's actually being depressed. And that's the whole idea of freezing point depression, is the freezing point is going to start a little lower. It's going to start a little lower, but then it's also going to drop as it goes. So it's no longer going to be a flat line. And that's super important to understand. So as the solutions freeze, what you would see is you might still have some supercooling. If you notice this part right here, that's a little bit of supercooling. But you can see that these two solutions, forgive me, I'm colorblind, so I can't tell if this line is orange or green, I'm not sure. But the light colored line, right, you can look here and say, well, it's starting to freeze in this general region right here. Like that is the general area in which it's starting to freeze. So if I think about that area right there and I go over to the side, I can actually get the freezing point of that solution. And I can get, if I look at this point right here being my freezing line as well, I can get the freezing point of that solution. Now, on this graph, it doesn't show you which is solution 1 and which is solution 2, But that's part of your job to understand. Obviously, one of these solutions has a much lower freezing point than the other one. They both have lower freezing points than water did, right? And we'd expect that. Because these solutions have solute dissolved, the solute disrupts the crystallization process. So you need to ask yourself, which solution would have a higher freezing point and which would have a lower freezing point based on their molalities, right? You know this to be true, right? You know that the change in temperature of the freezing point is the product of the Van Hoff factor. And think about ethylene glycol, right? The Van Hoff factor, this right here, I. We know ethylene glycol. This is the formula. So think about whether that's ionic or covalent, and you should be able to determine what the Van Hoff factor would be for that, the I factor. K is given. You always know K for a water-based solution. And then molality, you're going to be able to figure out the molality because you're going to have the delta T from the graph. Okay, so you're going to have to estimate what this change in temperature is for solution 1 and solution 2. Given that information, you should be able to realize which line on the graph is solution 1 and which line is solution 2, simply because you know that one of them is a weaker concentration and one of them is a stronger concentration. All right. Again, I don't want to give away too much. I feel like I have given quite a bit away already. But I'm trying to give you a little bit of baseline so you can go back and look at this video, listen to this video again, and hopefully it'll help you analyze the data and crunch the numbers a little bit, okay? What we would like you to do for sure is to write on the line on this graph which solution number it is, okay? So before you submit the lab, we want you to definitely tell us whether that's solution 1 or solution 2 on those graphs. Okay, or on the graph, the lines on the graph. And then once you get these two right here, right, these two values you can get from the graph. You'll have to estimate them. That's the best you can do. But once you get those values from the graph, you should then be able to plug your delta T in. You have the I, you have the K. You should be able to solve for the molality for solution 1 and for solution 2. Okay. Now, getting molar mass from the solution data, it's a little trickier. We've actually done a few examples of finding molar mass from molality, or finding molar mass from freezing point in class. But remember, right, just basic steps is you know that molar mass is grams per mole, right? Well, think about the grams. You actually know the grams. You know the grams in solution 1. You also know the grams in solution 2. So you can actually calculate the molar mass using the grams of solute that are given to you in the introductory to the lab, the way we created the solutions. The thing is, you're going to have to somehow figure out moles, right? How do you get moles? Well, remember, molality is moles over kilograms. Okay. So you'll be able to get the moles. You'll be able to get the moles because you are going to have you're going to have molality from the previous page. You'll have it right here. Okay. And kilograms, the kilograms we actually know from the way the solution was prepared. We know the kilograms of solvent that we used. So it turns out we can actually get molar mass if we have grams and moles, and we know the grams and we can get the moles from molality, which means we just have to get molality somehow, and that's actually pretty simple because you have it right here. Okay. So that's from number 5, right? Number 4 and 5 on the previous page. Hopefully, when you get these two values for the molar mass, think about it. It doesn't matter how strong you make the solution. It doesn't matter whether one solution is stronger than the other one. These two values here, hopefully these two values are similar because the molar mass of a substance should not change. Also, the goal is when you average them, right? So you're going to average those two values. And hopefully, when you get an average, right, it's pretty close to what the periodic table says it is. Okay, so I want to reiterate that number 9, this guy right here, number 9 is from the periodic table. Everything else, right, 8 all the way through number 1, 1 through 8, those are all from the data in your lab. You should not be using the periodic table at all for that. Okay. And then obviously there are some analysis questions here at the end. It's asking you in one of these to recall, right, what the cooling curve looked like for water. Remember, this is for pure water. Okay, and if you look at the graph we have supplied you, there's actually 3 lines on that graph. Only one of those lines deals with a pure substance. The other 2 are solutions, right? So it should be pretty self-explanatory. Hopefully that makes sense to you. And then obviously a few questions for you to work through. And so I hope that introduction is helpful to you. I know it could be a little a little spotty at times, but the good news is this is a video that on YouTube that you can go back, pause, and listen to it again, watch it again. So my suggestion would be please update your PDF as you watch the video. Honestly look through the procedure again and just familiarize yourself with the steps you would have taken if you were doing the lab, and then follow through step by step with the guidance I've given you, and hopefully you'll get a pretty decent value for your molar mass of ethylene glycol, otherwise known as antifreeze. Okay, that's all. As always, if you have any questions on the lab, you can certainly email your teacher, or you can log into one of the Zoom sessions that we have told you about. So, okay, I wish you the best of luck. Thanks for listening, and good